Brian Walker with Copper Mountain Technologies. Today I'm going to do a little demonstration of a 75 ohm measurement with a 50 ohm VNA. And it can be done. So let's talk about how that is done. For calibration, a vector network analyzer, a VNA, is always calibrated by the user before making precision measurements. Short, open, load, and through calibration standards are measured, and the results are compared to known values provided by the calibration kit vendor. Measurement correction is calculated from the comparison between the measured and the known values of the calibration kit. So the vector network analyzer is always calibrated by the user before making the measurements, and each calibration kit is defined by a table as shown below. You can see here that this kit is a 75 ohm calibration kit, which I'm going to use. It has shorts, both male and female. It has load, female only, I think. Yep. And it has a couple of throughs defined. I'm going to use the unknown through in this case. Unknown through is preferable to a known through in most cases because it doesn't have to be a particularly good through. It can have some loss. It could be, in fact, you can use a 10 dB attenuator if you want to. So unknown through is usually a superior way to do SOLT calibration. So this table of VNA is informed that the load standard is 75 ohms. You can see by the red box I have here. Even if the VNA internal hardware and port connector are 50 ohms, as is the case for this VNA I have on the table, it's still possible to calibrate to a 75 ohm system. I have here an SC5090. This is a 9 gigahertz 2-port VNA. And it is 50 ohms. So there are two methods to convert this measurement from 50 ohms, which is the VNA is natively 50 ohms, to a 75 ohm measurement. We can use a mechanical conversion, and we can do a mechanical plus LPAD matching. So I have here on the table a couple of mechanical converters. The male part on this end is 50 ohms. There'll be pictures here in the slides. And the other side is female 75 ohms. So these are both end connectors, but one side is 50, the other side is 75 ohms. The 75 ohm female is also designated by the yellow band. And 75 and 50 ohm end connectors are physically different. So let's be very clear about this. The center pin of the 50 ohm end connector, that's this side, is larger than the 75 ohm equivalent. Warning, attempting to connect a 50 ohm male connector to a 75 ohm female end connector will destroy the female connector. So it's very important to understand which side of your converter, your LPAD or your mechanical converter, which side is 50, which side is 75 ohms. You can tell by looking at it. As you can see in the picture here, the 75 ohm connector has a much smaller female, and the 75 ohm male has a much smaller pin. So the matching pad, which I have connected to the VNA at the moment, converts 50 ohm to 75 ohm. The resistive LPAD here provides a broadband match, but has a loss of 7.5 dB. And you can see here, this is what's inside of it. I have a 50 ohm source in my schematic depicted here. And inside this LPAD is an 86.6 ohm to ground and a 43.3 ohm series resistor. That looks like 75 ohms from the right-hand side, and it looks like 50 ohms from the left-hand side. So this accomplishes the change mechanically from 50 ohms to 75 ohms. This matching pad has a 50 ohm male connector in, and it has a 75 ohm female end connector on the other side. Connected to it, I have a pair of 75 ohm cables because I have two of these matching pads. I'm going to show the difference between using the matching pad or using the mechanical converters. The matching LPAD is preferred as it provides a good match in both directions. If you look into it, if you look at a 75 ohm load with a VNA, you're going to see good return loss even before you calibrate. So raw source and load match errors, in this case, will cause small ripples, or can cause small ripples in transmission tracking. Now what's going on here is that the raw source and load match is 14 dB if you use a mechanical cal kit, or mechanical converter. So if the 50 ohm VNA has this converter on here, and then it sees a 75 ohm load, there's going to be a 14 dB return loss immediately. And the source match into a 75 ohm system is going to be 14 dB. The load match on the other side similarly is going to also be 14 dB. So that's a pretty poor source of load match. Very often they're 20, 25 dB or better. So 14 dB is not so good. The transmission tracking error, there's an estimate of transmission tracking error is the raw source match multiplied by the residual load match plus the raw load match multiplied by the residual source match in this equation I have on the screen. And if I use 12 dB or 14 dB as for 75 to 50 ohms, I get plus or minus 0.11 dB as an expectation of transmission ripple making a transmission measurement. Now, I may not see that, and in practice I probably won't, but this is an estimate of how bad it could be. So there are frequency considerations for 75 ohm measurements. They mostly only operate to 3 gigahertz, which was adequate for cable TV purposes. And many 75 ohm cables are also somewhat frequency limited. So in some implementations, a 50 ohm cable might be used, connected to the VNA directly to the port. And then at the end of the test cable, 50 ohm test cable, I use the opposite of one of these, which is female 50 on one side and male 75 on the other end. And I would connect that to my 50 ohm cable. And now I would perform 75 ohm calibration at the end of my 50 ohm converted cable. And that way I might get a better frequency response if needed. So be sure to get the right gender of the pad. The other possibility, here I have N connectors. The possibility is also to use F connectors. Those are common in cable TV. They're really only rated to 3 gigahertz. The load standard uncertainty of 36 dB for an F type calibration kit might be typical, which isn't great, but it's not too bad. But F connectors are really not metrologically sound. The center pin of the F connector is the center conductor of the cable. It's not very stable. And just all around, it's not the greatest kind of connector. If you have to use it, you do. But if you have a choice, I would use the N connectors if possible. So let's do a demonstration. I brought up my S2 VNA. This is the program that operates my VNA here, my 9 gigahertz VNA. And attached to my VNA, I have the 2 LPAD converters. I have 2 50 ohm cables. 50 ohm to 75 ohm converters, LPADs. I have 2 75 ohm cables. And then on the, for my device under test, I have a 470 megahertz filter. It has F connectors, so I have adapters on here to go from N female to F male and connect to it. So I have previously calibrated this VNA, and you can see here that I'm able to measure the filter quite well. I have a pretty low loss on the top. I'm showing the pass band, stop band, and the return loss of this filter. The bottom pane is showing a close-up of the insertion loss of the filter, and I can see that it has a loss of about 470 filter, so it's probably about a dB of loss at 470, and it has a little bit of ripple, about 0.2 dB of ripple. And this was with calibrating using the LPADs. I also connected the mechanical adapters and performed calibration once again and measured the same filter. And I did this in another channel, which I have set the trigger to hold, so I can compare the two measurements. So let's do that. So I will do the calibration with mechanical adapters instead of the LPADs. I should mention that the LPADs, while they do provide a good 75 ohm broadband, 75 ohm, 1575 ohm match, they do have about 7.5 dB loss each side. So you will lose 15 dB of dynamic range if you are using these. whereas the mechanical converters have essentially no loss. So now we are ready to measure the filter and compare it to the LPAD results. And I would say, just by looking at this, that the results are identical. Even though I said there could be more transmission tracking error due to the poor source and load match, raw source and load match, due to the 50 ohm source load in a 75 ohm system, I'm not actually seeing the effects of that. So I think that's a worst case prediction. I think for the most part, if you use the mechanical adapters, you're going to be fine, and you'll get good measurements. Particularly if, as this one customer needed to measure up to 12 gigahertz, using a 50 ohm cables that were capable of measuring 12 gigahertz, and putting the mechanical adapters on the end of the cables. The point here is that you can measure 75 ohm systems with a 50 ohm VNA. You do need to do some mechanical conversion because the cables and the connectors are slightly different. You can use the LPADs, which will give you a more appealing return loss presentation on your screen, or you can use the mechanical adapters. Either way will work just fine when you go to make your measurement. Thank you very much. That's all I had for today.